Swayam Prabha. Digital India. Educated India.
Now, we are going to discuss how to solve one numerical example related to the multi-layered the feed forward network. Now, here I am just going to show a small network. So, before I read this particular statement, so I am just going to show a small network. Now, this network is nothing but actually a 3-layered network. Now, on the input layer we have got say 2 neurons, on the hidden layer we have got the 3 neurons, and on the output layer actually we have got 1 neuron. So, this is nothing but a 2-3-1 network. And now, I am just going to show and I am just going to state the statement, going to give the statement of the problem. Now, we will see that. So, this is the schematic view of this multi-layered feed forward network, and it consists of 3 layers like your input layer, hidden layer and the output layer. The neurons lying on the input, hidden and output layer have the transfer function represented by y equals to x on the input layer, that is the linear transfer function, y equals to 1 divided by 1 plus e raised to the power minus x. So, this is nothing but is your log sigmoid transfer function, and y is nothing but e raised to the power x minus e raised to the power minus x divided by e raised to the power x plus e raised to the power minus x. So, this is nothing but the tan sigmoid transfer function. There are 2 inputs I 1 and I 2, and there is only one output, that is O. The connecting weights between the input and the hidden layers are denoted by V, and that between the hidden and output layers are denoted by the W. Now, the initial values for these particular the connecting weights are shown here. Now, here you can see that is V 11 is nothing but your 0.2. That means, the connecting weights between the first input neuron and the first hidden neuron, that is V 11 is 0.2. Similarly, V 12 is 0.4, V 13 is 0.3, 21, that is between the second neuron lying on input layer and the first neuron lying on the hidden layer is nothing but is your 0.1, V 22 is 0.6 and V 23 is nothing but 0.5. Now, similarly, the connecting weights between the hidden layer and the output layer, that is W 11, that is the connecting weight between the first hidden neuron and the output neuron is 0.1. The connecting weight between the second hidden neuron and the output neuron, that is W 21 is 0.2. Similarly, W 31 is 0.1. And here we have got a large number of training scenarios, and out of all the training scenarios, supposing that say I am just going to show only one. Now, the training scenario is something like this: if I 1 is 0.5 and I 2 is minus 0.4, then output, the target output is nothing but 0.15. Now, we are going to use the incremental mode of training, and using this incremental mode of training, so we are going to find out what should be the modified value for this V and the modified value for this particular the W. So, our aim is to determine the changes the values changes in the values of V and W during this particular the training, and we are going to consider the learning rate, that is eta is 0.2, and for simplicity actually the momentum constant, that is alpha prime, has been taken to be equal to 0.0. That means, we did not consider the momentum term, and through hand calculation we are going to show one iteration of this particular the network. Let us see how does it work. Now, before I go for this particular solution, let me once again look into this particular network. So, it is a very simple network. So, what we do is, here we have got two inputs and one output. These are the connecting weights, and here we have got the transfer function like y equals to x, and in the hidden layer actually I have got the log sigmoid transfer function, that is 1 divided by 1 plus e raised to the power minus x, and on the output layer we have got the tan sigmoid transfer function, that is nothing but e raised to the power x minus e raised to the power minus x divided by e raised to the power x plus e raised to the power minus x. And this learning rate some value we have assumed, and the moment I pass one set of training scenario. So, I will be able to find out what is the calculated output. Now, this calculated output will be compared with the target, the error will be determined, and this error will be propagated back for the purpose of updating the connecting weights, so that this particular network can predict the output for a set of inputs more accurately. Now, let us see how to carry out these particular calculations and how to find out the change in V and the change in W values in order to minimize the error in prediction. Now, the way it has to be solved, this I have already discussed. Now, let me repeat. So, what we will have to do is, in the input layer we are using the linear transfer function of the form y equals to x. So, output will be nothing but the input. Now, here the same symbol I am just going to use the same nomenclature. For example, say I01 is nothing but the output of the first neuron lying on the input layer is nothing but I1, that is the input of the first neuron lying on the input layer is nothing but 0.5. Similarly, I02 is nothing but I2 is nothing but is your minus 0.4. So, these are nothing but the outputs of this particular the input layer, and once you have got this particular output, now the respective outputs actually we are going to multiply by the connecting weights, and we can find out like what should be the input of the different neurons lying in the hidden layer. For example, say HI1, that is input of the first neuron lying on the hidden layer is nothing but I01 multiplied by your V11. Now, this I01 is nothing but the output of the first neuron lying in the input layer, and this is multiplied by the corresponding connecting weight, that is V11 plus I02 multiplied by V21, and if you calculate you will be getting 0.06. Now, similarly, this HI2 is nothing but I01 multiplied by V12 plus I02 multiplied by V22, and that is nothing but minus 0.04. And similarly, I can find out HI3, that is nothing but the input of the third neuron lying in the hidden layer, and that is nothing but I01 multiplied by V13 plus I02 multiplied by V23, and that is nothing but minus 0.05. And once you have got these particular inputs of the hidden neuron, now very easily we can find out what should be the corresponding output. Because we have got, so this particular transfer function, that is your the log sigmoid transfer function, and that is nothing but y equals to 1 divided by 1 plus e raised to the power minus x. So, this particular x is actually I will have to put the input of the different hidden neurons. Now, this H O 1 is the output of the first neuron lying on the hidden layer, and that is nothing but 1 divided by 1 plus e raised to the power minus h I 1. And if you put this numerical value and solve, there is a possibility that I will be getting this particular the output. Similarly, the output of the second neuron lying on the hidden layer, using this particular expression I can find out, that is your 0.490001, and by following the same I can also find out what is H O 3, that is output of the third neuron lying on this particular hidden layer, and this is nothing but this, and this is your 0.487503. So, this is the way actually we can find out what should be the output of your different hidden neurons. And once you have got, so this particular output, we can find out what should be the input of the neuron lying on the output layer. So, this O I 1 is the input of the first neuron, but on the output layer we have got only one neuron with rest lying on this particular the output layer. So, O I 1 is nothing but the output of the first neuron lying on hidden layer multiplied by W 11 plus H O 2 multiplied by W 21 plus H O 3 multiplied by W 31, and if you insert the numerical values and calculate. So, you will be getting this is nothing but the calculated output of this particular network for this set of inputs. And once you have got, so I am sorry, so this is nothing but the input of the neuron lying on the output layer. So, if I know this particular input, so I can find out what should be the output of this particular neuron lying on the output layer, and here actually we have got your the tan sigmoid transfer function. And for this tan sigmoid transfer function, so this O I 1 is nothing but this, and if I just put these numerical values here and if you calculate, so I will be getting the calculated output of the neuron lying on the output layer is nothing but this. Now, if you know this calculated output, so very easily we can find out what is this error. So, this error in prediction is nothing but half T O minus O O 1 square, and if you calculate, so you will be getting this particular as the error, and based on this particular error actually I will have to do your the updating. Now, let us see how to update. So, this particular connecting weight, that is your W 11. Now, this W 11 is actually nothing but is your, so this particular thing. So, this is your W 11. So, I am just going to update. So, I am just propagating back. So, this particular error, and I am going to update this particular the connecting weight. Now, let us see how to update this particular the connecting weights. Now, to update the connecting weights, we are using in fact your the back propagation algorithm or the delta rule. Now, according to this delta rule, so the change in W 11, so delta W 11 is nothing but minus eta, the partial derivative of E with respect to your W 11. Now, the partial derivative of E with respect to W 11 is nothing but partial derivative of E with respect to O O 1 multiplied by the partial derivative of OO1 with respect to OI1 multiplied by the partial derivative of OI1 with respect to your W11. Now, here we have already discussed like how to find out. So, these partial derivatives, for example, say your this partial derivative of E with respect to O1 very easily can find out this particular expression. Then comes your this partial derivative of O1 with respect to your OI1, and here we have got actually the tan sigmoid transfer function. Now, if you just for example, say if you write down the expression for tan sigmoid, so e raised to the power x minus e raised to the power minus x divided by e raised to the power x plus e raised to the power minus x. So, very easily actually we can find out what is dy dx. This I have already discussed. Now, if you find out the dy dx, then with a little bit of simplification, so you will be getting this particular the expression. So, this is nothing but the partial derivative of OO1 with respect to OI1 is nothing but this. Then partial derivative of OI1 with respect to W11 is nothing but HO1. And once you have got all the terms, so now actually what you can do is your we can multiply just to find out what is this your partial derivative of E with respect to your W11, and we also put actually the value, the numerical value of the learning rate. And once you have got this particular thing, so very easily we can find out what should be this change in your W11, that is change in W11 is nothing but minus 0.004526, and once you have got it, very easily you can find out your W11 updated is nothing but W11 previous plus your delta W11. Now, this delta W11 we have already got. So, very easily you can find out the updated value for this W11. Now, the same principle we are going to use for determining what should be the updated value or what should be the change in W21. So, change in W21 will be minus 0.004306, then change in W31 is nothing but minus 0.04284. So, by using the same principle we can find out what should be the change in W values, and once you have got, now we will have to find out the change in V values. So, this V11 is nothing but the connecting weights between the first neuron of the input layer and the first neuron of this particular the hidden layer. So, delta V11 is nothing but minus eta partial derivative of E with respect to your V11. Now, the partial derivative of E with respect to this V11 is nothing but your partial derivative of E with respect to OI1 multiplied by the partial derivative of OO1 with respect to OI1. Then comes your the partial derivative of OI1 with respect to your HO1, then partial derivative of HO1 with respect to HI1, then partial derivative of HI1 with respect to your V11. And once again we are going to use the chain rule of differentiation. Now, this partial derivative of E with respect to your OO1, so I can find out this particular expression. Then comes your the partial derivative of O with respect to your OI1, this we have already seen. So, we can find out. The next is your the partial derivative of OI1 with respect to HO1 is nothing but W11. Then partial derivative of H01 with respect to Hi1 is nothing but e raised to the power minus Hi1 divided by 1 plus e raised to the power minus Hi1 square. Now, this is nothing but is your the log sigmoid transfer function, and it is of the form 1 divided by 1 plus e raised to the power minus x, and we have already discussed that this can be determined, this particular derivative can be determined. And once you have got this particular derivative with little bit of simplification, so you will be getting this particular the expression. And your the partial derivative of Hi1 with respect to V11 is nothing but I01, and once you have got all the expression, now you can put together and we can write down. So, this expression of partial derivative of E with respect to V11, and if you put all such numerical values in that particular expression, so you will be getting the partial derivative of E with respect to V11 is nothing but 0.00549, and once you have got this, very easily you can find out what is your delta V11. So, this delta V11 actually we can find out, and once you have got this delta V11, now we can find out what should be the updated value for this is your V11, because V11 updated once again is your nothing but V11 previous plus your delta V11, and we can find out what is this V11 updated. And once you have got, by following the same principle, we can find out like what should be your the change in V21. Now, the change in V21 is something like this, then change in V12, change in V22, change in V13, change in V23. So, all such numerical values we can find out, and once you have got all such numerical values, now actually we are in a position to find out the updated values for this particular your the network in one iteration. Now, if you see the updated value, so the updated value for this V11 will become 0.199890. Similarly, the updated value for V12 is nothing but this, V13 is nothing but this, then comes your V21 updated value is this, V22 the updated value is this, and V23 the updated value is something like this. And I can also find out like the updated values for this W, that is your W11, the updated value will be something like this. For W21, the updated value will be something like this, and for W31, the updated value for this is something like this. Now, once you have got, so these particular updated values, and I am using say the incremental mode of training. So, I can find out these updated values, and using the updated values, once again if I pass the same set of training scenario, there is a possibility that I will be getting a slightly less error in prediction, and supposing that I am running for say 10 or 20 iterations following the same principle, before I go back or before I start with the second training scenario. So, based on the first training scenario, let me update or let me update say 10 times, or let me just run this for say 10 times, 10 iterations. Then we go for the second training scenario, repeat the process, then you go for the third training scenario, you repeat the process, and all the training scenarios you pass one after another, and at the end of passing each training scenario, you update this particular the network. Now, if you follow this particular method, there is a possibility that you will be getting one network, the optimal network or the near optimal network after passing the 10th training scenario, and whatever you got after passing the first training scenario, there could be a lot of difference. So, these two networks could be different performance wise, and if you follow this incremental mode of training, there is a possibility that you may not get a very good generalization capability of this particular the network. The network may not be adaptive in nature, and if it is not adaptive in nature for the unknown test scenario, so this particular network may not work well, particularly if you just go for the incremental mode of training, which is computationally very fast compared to the batch mode of training, but its generalization capability may not be sufficient. Thank you.